in Canvas tonight by 11:59 the worksheet that is titled "Do Seatbelts Work Better Than Your Face in the Windshield?" as well as practice problems. So in Canvas, under S2 for semester 2 in modules, I have it published under today, and it says "Do Seatbelts and Practice Problems" worksheet. So there's 2 PDFs because it's 2 separate pages, but the idea is take a picture, submit it. So if you have it done, I'll give you, while I take attendance, take time to go through, take those 2 pictures. There's 2 sides, the front and back, from that worksheet. Get that turned into Canvas right now. Some of you, you had some work time on Friday. I know some people had it done and were asking, like, what do I do with this? And I said, hang on to it. Now I want you to submit it in Canvas. So, in Canvas, under modules, it's called "Do Seatbelts and Practice Problems." That's the one. Take your 2 pictures of your 2 completed sides. If it's done, if it's not done, hang on to it. And then I want it done and posted in Canvas by tonight. And I don't remember if I talked to you. I feel like I didn't talk to your class. It was the one I missed. If I did, stop me. If not, I'll tell you. I'm part of a group that meets with Mr. Rather on a fairly regular basis, and we talk about things with the school. And one of the things that we as that group is trying, we agreed to try, is we as a teaching staff feel that we have some issues with deadlines, and we don't do a good job of reinforcing that deadlines are important and deadlines matter. So this semester, I will be mindful with the due dates that I set, and I'm going to be reasonable. I'm not going to give you something that's going to take hours and hours and say, hey, this is due tonight. I'll respect that, but the due dates that I set in Canvas are the due dates, and I am not going to grade late assignments if they are turned in after the due date, unless there's an unless. But we are saying that deadlines are important and deadlines matter. So I am going to, Canvas is set up to automatically enter a 0 if you do not have your things submitted in on time. And I will not look at them after that point. Okay, so if you turn it in late and Canvas shows me that they're blue means missing. No, blue means late, red means missing. So if they're missing as of 11:59, because that's when my due date tends to be, at 11:59, automatically a 0 gets entered for it, and I am not going to grade it, and it will remain a 0 for the entire semester. Unless we are going to try this. There is going to be a form, it's called Late or Incomplete Assignment Application Form. So if you are going to, if you submit something late, and you would like to receive credit for that late work, there's a form that you will fill out for each and every assignment and lab that is. Now labs would be important because those are S8, that's this content standard ones in particular. But your name, class, missing assignment, original due date, reason for missing the due date, what was your reason for it, some details, when you revise completion date, what are some things that could help you to not have this happen again, and then in order for your assignment to be accepted, you must fully complete the above and set up an appointment with your teacher during ELT. So you got to talk to me during ELT about this. Your teacher must give you permission for the assignment to be turned in late. The teacher may deny your application for submission of the assignment if they so choose. All applications must be submitted within 1 week of the due date. The teacher then, if on acceptance, I will grade it as if it was for full credit. So, early on, I'm going to be probably a little bit more forgiving. We're going to go through this and we're going to talk about it and we're going to say, hey, why didn't you do this? But if it becomes a regular habit, we're going to start having some of those conversations, and there will become a time that down the road, like, hey, this is a 5th, this is a 10th, this is a 20th time we've been talking about why you didn't have it in on time. I'm going to start saying, no, I'm not taking it. Okay, I'm making up arbitrary numbers just for the record right now, but keep that in mind. So due dates matter, and I'm not going to grade them unless we fill out that thing. Then, if I agree to it, and we talk about it, we talk it through, I'll grade it as if it was full credit. Also, this is going to be something we'll try too, an application for a retake on an assessment. So if you would like to take a retake on an assessment, what part do you want to retake? What is the reason you were not successful the first time? This is some kind of guided self-reflection. What actions are you going to accomplish before you retake the assessment? In order to retake the assessment, the following checklist must be completed. All of the homework must be turned in for that unit. Form must be completed and submitted within 1 week of the original assessment. And then you must initiate a conference with the teacher during ELT, and then again, we'll talk about it with an approval process. Okay, so something we're trying second semester. I'm part of that group, and they said, hey, something's not going right. Let's try to see if this is going to be better or not. And if it's absolutely terrible, we'll move on and we'll kind of try something different. But that's that, and I don't think I mentioned this to you before. So it is something that we are going to try. So make sure when I talk about due dates that you get those things in and you get them in that time. Your egg drop labs, I just went through and I put in. I messaged those of you who were absent with a link directly to the assignment because there's a YouTube video for you to watch so that you can get instructions on how to do the egg drop without actually being here. So if you were gone for the day of the egg drop, make sure you take care of that. So let's take a look at this little sheet of paper that you picked up on the way. Part of the momentum problems that we're going to be working on are these three. P is equal to M times V, delta P is equal to P2 minus P1, delta P is equal to F times delta T, which is equal to impulse. Those were the equations the first three equations that we kind of dealt with last week. Right on the end of the week, on Friday, I introduced conservation of momentum that says sigma P1 is equal to sigma P2. The sum of sigma, my momentum, P times V, at location 1 is equal to sum of my momentum at location 2. So when we talk about types of momentum, types of momentums, I should say, we want to identify types of collisions or interactions. So I call them collisions most of the time. 3 out of the 4 are collisions, but one of them isn't really a collision, so that's why I kind of slash it as an interaction. So this little sheet is meant to be a good reference sheet for as we're going through and we're discussing these, for you to kind of be thinking through, because this will kind of help us set up the problems and identify what we have. So as we go through, some of the questions, there are going to be some questions that will just ask you, like, what kind of collision is this? What kind of interaction is this? Those are kind of the concept style questions that you'll see on tests, and that's what this is doing. So on Friday, we started with that astronaut floating in space holding a wrench, throws a wrench in the opposite direction, and drifts back to the spaceship. This is a recoil interaction. So that's the one that's not really a collision, it's more of an interaction. But it's an interaction where two or more, I guess, objects start together and they end apart. They start together and they end apart. So the person, the astronaut, and the wrench, they throw. They start together, they end apart. A bullet in a gun. You fire the bullet out of the gun, the bullet comes flying out, the gun pushes backwards. You could stick like a firecracker in a snowball, and you could ignite it, and the snowball is going to go and fly in all directions. That'd be a recoil. It would just be more than 2 objects. But they start together, and they end apart. Now, when I talk about something being deformed, in my mind, anything that is deformed looks different than it started. If it does not look exactly the same as when it started, then there is deformation, or the object was deformed. So considering they start together as one object and they end apart as different objects, I would say that those do not look exactly alike. Therefore, yes, those objects were deformed. A bullet comes flying out of the barrel of the gun. Well, that bullet was in a brass cartridge. They look different before and after. So there was some deformation. My wonderful and amazing pictures that I draw for these can be blocks. So we start together as a object. So I draw a box with object AB. That's my before. They start together and they end apart. They end apart. Now we draw arrows. You know, this object might be moving to the right, before it might be moving to the left. This one might be moving right, this one might be moving left, kind of depends upon the situation. The idea of is momentum conserved is basically this idea, can I use the equation that I just wrote on the board and I'm writing up above, sigma P1 equals sigma P2. And if momentum is conserved, I can use this equation. Just for the record, all four of my momentum conservation collisions and interactions, all four of these have momentum being conserved, which means we can use this equation for all four of my interactions. Kinetic energy is something that we will address when we need to, but kinetic energy is not conserved in a recoil interaction. The only reason we even care about kinetic energy being conserved is those bottom two are almost identical, and that kinetic energy being conserved is a clarifier that we can use to determine whether it's elastic or partially elastic. So that's why that column is there. But they start together, they end apart. That's a recoil interaction. Lots of variations of that. Driving down the road, your trailer falls off, you started together, they end apart. That's also very bad, not good. Okay? But that's would be considered a recoil because they start together, they end apart. An inelastic collision is the opposite of a recoil. So a recoil is where they start together and they end apart. Inelastic is where they start apart and they end together. So when I think of this, I think of elastic being if something is very elastic, it's pretty bouncy. Okay, so elastic, they're going to bounce off of each other. If something is inelastic, it's not bouncy. So what happens is they stick together when they hit. That's the way I kind of remember this. So inelastic is the opposite. An inelastic collision is where an object starts apart and ends together. They start apart and they end together. Because these are not exactly the same, an object that starts apart but then two objects start apart and stick together, those are deformed per my definition. They look different at the start than they did at the end. So I have two objects that start apart, object A and object B, but after the collision, they stick together. Yes, momentum is conserved. No, kinetic energy is not. Now again, with my pictures, I would draw arrows. So if two objects start apart, are they moving towards one another? And we draw arrows pointing towards each other. They're moving the same direction, they're moving in opposite directions, and they're moving towards each other. Is it a head-on collision? Is it a car like rear ends another car because object A was moving faster than B and catches up to it even though they're moving in the same direction? But the idea is they stick together. So some car collision problems would be like if two cars collide and they say like their bumpers lock, means they like stick together and they get stuck. They move together as one. If I were to take like a lump of clay and I were to throw it on like into a bucket, and then the bucket and the clay were to move off together as one. If you were sitting on a scooter, like one of those scooters from Fayette classes, and someone were to throw a medicine ball to you and you caught the medicine ball while on the scooter, you and the medicine ball would move off together as one. That would be an inelastic collision. That's some examples of that. In elastic, so inelastic, not bouncy, elastic, bouncy is how I kind of think of it, very bouncy, elastic. In elastic collision, an object's going to start apart and it's going to end apart. The objects that start apart look identical to before as they did after. There is no deformation. There is no deformation. So we start with two objects apart, object A and object B, and I end with two objects apart, objects A and object B. And again, I have arrows. Are they going towards each other? Are they going opposite directions? Did they bounce? Are they both moving together in the same direction? Did they bounce opposite directions? All that. So with our arrows, we assign positive and negative velocities because that gives us positive and negative momentum. Keep that in mind. Yes, momentum is conserved. And the thing here is this is how we can identify or clarify whether it's an elastic collision or not, is if kinetic energy is conserved. And that's going to be like the very, very last piece that we'll add at the end of this unit. We can go through and do conservation of momentum without addressing whether it is elastic or partially inelastic. We can do the momentum piece without that, but that's like the last thing, it's a clarifier. Partially inelastic is very similar to elastic. Oh, and just for the record, traditional physics and AP physics use slightly different names for these interactions, so just so you're aware of that, if you ever talk to someone, they call them slightly different things. But they also start apart, and they end apart, just like the one above. However, kinetic energy is not conserved. And in terms of deformation, I'm going to put yes/no, because it kind of depends. So let me talk about some examples of this. An example of a start apart, end apart collision would be two cars are at the four-way stop. They confuse what's going on. I don't know. Actually, this is a terrible, because it'd be really kind of weird to have a head-on collision at a four-way stop sign. So maybe a bad example. But whatever. Two cars collide head-on. They start apart, they bounce off, they smash, but they bounce away from each other. That's a start apart, end apart collision. In terms of deformation, the fact that the front ends of those cars are smashed, yes, there is deformation, therefore it's a partially inelastic. I know that because there's deformation. The idea of deformation is it's going to absorb some of that kinetic energy. So when we talk about is kinetic energy conserved, the answer is no. It's because during that deformation, the crumpling of that car, some of that kinetic energy was absorbed and converted by design in terms of cars. Okay, so that for sure is a partially inelastic collision. So any two objects that start apart, end apart, and they get deformed in the process, partially inelastic. If they start apart, end apart, and there is no deformation, then it's one of the last two. Okay, so an example of two objects that start apart and end apart, and there's no deformation. Visually in my mind, the best one that fits this is the game of pool. So if you take a cue ball, and the cue ball strikes the 8-ball, the cue ball looks exactly the same before and after. The 8-ball looks exactly the same as it does before and after. There was no deformation in the process. So there was no deformation. It's either elastic or partially inelastic. So then in order to determine which one it is, we'd have to do the kinetic energy calculation that we'll do at the end. The idea is no kinetic energy is lost in the process. It's simply like converted straight into the next one. That's really a hard thing to happen in real life. Because even those two, the cue ball and 8-ball, when they hit, there's a sound, there's a little bit of heat generated, some of that kinetic energy, a little bit of kinetic energy will be lost in that process. So it's a tough thing to actually have a perfectly inelastic one, but it's kind of the clarifier. So just so you're kind of aware of that. So using this kind of chart, we can kind of identify some of the problem types and the types of collisions that we have. So we're going to go through 2 of the 4 collisions today. We already did one of them. We're going to redo one just to kind of keep practicing. And it's on the worksheet called In-Class Momentum. So on Friday, we worked through the problem number 3 called on In-Class Momentum, and it was called, I shouldn't say it was called, it was the one about an astronaut throwing a wrench floating in space. That was an astronaut who's holding a wrench. They start together, they throw the wrench in the opposite direction, so they start together, they end apart. That was a recoil interaction. So we're going to take a look at in-class momentum worksheet. We got it, I think, last week Tuesday is when we got this worksheet. And we're going to look at problems number 4, and then we're going to look at problem number 5. So problem number 4 on the worksheet called In-Class Momentum is looking at 2 people on roller skates. So 2 people on roller skates are standing still next to each other. They then push off of each other, causing them to move in opposite directions. Skater A has a mass of 80 kilograms and skater B has a mass of 65 kilograms. After they push off, skater A has a velocity of 1.2 meters per second. What is the velocity of skater B? So I probably improperly used the term they have a velocity. It probably really should be they have a speed of it, but we'll address that when we get there. So pictures are helpful. I really think pictures are helpful. I would draw a before and after picture with some amazing people pictures that I don't draw. I personally like to draw boxes because they're simple, but they get the point across. So we have 2 objects. We have skater A and we have skater B that are standing still next to each other. Next to each other. Location 1. Location 2, they push off each other, causing them to move in opposite directions. So they started A on the left, B on the right. So A is going to be moving this way, B is moving in the opposite direction. Skater A has mass of, skater B has mass of. After they push off, skater A has velocity of, what is velocity? Okay, so that's my picture. Now, this is going to be a conservation of momentum. The sum of all my momentums before is equal to the sum of all my momentums afterwards, or at location 2. This picture, I think, does a really nice job of kind of building that equation. I start with 1 object, I end up with 2 objects. What this really is going to be is the momentum of this thing is equal, this is kind of like an equal thing, this is equal to this plus this. And when I say this plus this, I'm really saying the momentum of this is equal to the momentum of this plus the momentum of this. The momentum of this, before, all my momentums before, I only have 1 object, so 1 momentum, is equal to the sum of my momentum of all my objects. I have 2 of them at location number 2. So remember that P is equal to M times V, so I'm going to have to find the momentum of this and this and this. So in my picture, I find it beneficial to go through and label mass and velocity for each and every object. Because if I know the mass of object A, B, and the velocity of object A, B before, I can find the momentum of object A, B before. Same thing with mass of object A, the velocity of object A after, mass of B, velocity of B after. Now I don't need to say M MA2 and MA1 because it's the mass of the object. The object in of itself doesn't gain and lose mass, so I don't really deal with that one. It says skater A has a mass of 80. Skater B has a mass of 65. So when they were together as one object, they had a combined mass of 145 kilograms, which in this problem doesn't really make any difference because it says they were standing stationary, they're standing still next to one another. So their initial velocity at location 1, or their VAB1, is 0. So the reason I said that doesn't really matter what their combined mass was is because mass and velocity gives you momentum, they have no velocity. And then it says after they push off of one another, skater A has a velocity of 1.2 meters per second. And I said I should maybe change that to have the speed of. That would probably be a better way to word that. Because velocity is speed with a direction, and it didn't give me the direction, it just gave me the speed. Per my picture, I drew my A arrow to the left. That means my velocity of my skater A needs to be negative 1.2 because I drew them moving to the left, the negative velocity. And it's asking us to solve for the velocity of skater B. Mass times velocity equals mass times velocity plus mass times velocity. That's what we're getting to. That's what this equation works out to be. The sum of, conservation of momentum, sigma, sum of all my objects' momentum, there's 1, at location 1 is equal to the sum of all my objects' momentum at location 2. There's 2 of them. So this is the momentum of object AB at location 1. There's only one object, so there's only one momentum, is equal to the sum of all my momentums at location 2. I have 2 objects, so I need to have 2 momentums, and it's object A at location 2's momentum plus the momentum of object B at location 2. 2 objects, 2 momentums. Remember, P is equal to M times V. So if I'm trying to find the momentum of object AB at location 1, I take the mass of object AB times the velocity of object AB at location 1. Mass of AB, mass times velocity gives me momentum. So at location 1, mass of AB times velocity of AB at location 1. That's equal to the momentum of object A at location 2. So to find the momentum of object A at location 2, we take the mass of A times the velocity of object A at location 2. That gives me PA2. Then I have to add that to the momentum of object B at location 2. That's the mass of B times the velocity of B at location 2. Our VAB1 was 0, so we have no starting momentum, which means when we sum up those two numbers, they also have to add up to 0. So now I'm just plugging in numbers from my picture, make sure we include that negative 1.2 meters per second, because per my picture they're moving to the left. So we get 0 is equal to negative 96 plus 65 VB2. Do not combine this number and this number, because this is times VB2. This has a VB in it. This one doesn't. They're unlike terms. So we have to add 96 to both sides. We end up with 96 is equal to 65 VB2. And our final VB2 is going to be a positive. It's going to be a positive, I don't 1.48 meters per second. And that positive is telling me it's moving to the right. I put a negative because it said it was moving. They start together, they end apart. That's a recoil interaction. It's the first one. They start apart, and then they. Last one I'm going to work through with you today is we're going to do number 5. Number 5 says a 60 kilogram person is running at 5 meters per second and they jump into a stationary shopping cart, 20 kilograms. How fast will the person in the cart move after the person jumps in? So I have a person who runs towards a stationary shopping cart, and then they jump in and they move off together as one object. Now, chances are pretty good that I can predict that if object A is moving to the right and object B is stationary and object A jumps into object B, that they collectively are going to move off. It'd be kind of weird if I'm running in this direction, I jump onto something and they start going backwards. That just doesn't work that way. So there's my quick picture. For each object, I want a mass and velocity for location 1 and location 2. So I need the mass of A, velocity of object A at location 1. Mass of B, velocity of B at location 1. That equals the mass of object AB times velocity of object AB at location 2. So, taking a look at the problem once again, 60 kilogram person, so this is my person, 60 kilogram person, that's object A's mass, jumps into a shopping cart, 20 kilograms. That means collectively they move off together, they're going to have a combined mass of 80 kilograms. If the person, for my picture, is moving in the positive direction at positive 5 meters per second, and they jump into a stationary, not moving, shopping cart, what is going to be their velocity afterwards? Conservation of momentum, I start with 2 objects. I'm going to have to add these 2 objects together to equal the momentum of this plus the momentum of this is going to equal the momentum of this. That's the idea of conservation of momentum. Sigma P1 is equal to sigma P2. I start with 2 objects. I start with object A. I start with object B. I end with object AB. So I need to have the momentum of A before PA1. I have to add that to the momentum of object B before PB1. And that's equal to the momentum of object AB at location 2. Momentum is mass times velocity, so mass of A times the velocity of A before, plus the mass of B times the velocity of B before, is equal to the mass of object AB times the velocity of AB after. Because my velocity of object B was 0, there is no momentum of object B before. So 60 times 5 is equal to 80 VAB2. So 300 is equal to 80 VAB2. Divide both sides by 300 divided by 80 is 3.75 for our final answer. Object AB, after the person jumps in, they will move off together at a positive 3.75 meters per second. They move go off to the right, positive 3.7. And hopefully, the fact that if a person jumps onto a stationary object, it would seem really odd that if you jump onto a stationary object that you're going to start moving faster than you did originally, right? Because some of that momentum is going to, some of that kinetic energy is going to get absorbed. So, this worksheet that I'm passing out is homework sheet for, I think I have it set for Wednesday right now. Honestly, I think if you get to, I'm not even sure what time it is. We got about 10 minutes. I'd say if you get to the bottom of the first page, I'd say let's stop at that point. That'd be kind of a good kind of checkpoint. The front side of this worksheet deals with the first three equations. Okay, P is equal to M times V, delta P is equal to P2 minus P1, delta P is equal to F times delta T. That very last one talks about like a cue ball and an 8 ball, but it gives you a force. So because it gives us a force, we're going to be using this. Now, it's not asking for what's the time, what's the change of P, it's asking what is the final velocity, which remember, mv2 minus mv1 is another way we can write delta P. So, the front side would be a good kind of checkpoint to be at for tomorrow. The back side has some collisions. I think they're more start apart, end apart type of problems. They're very similar, but that'd be a good kind of stopping point, I think. So, if you have any questions, let me know. I just realized that whole last problem that I worked on, the camera wasn't pointing at. So there you go, people. There's that second problem. Sorry about that. Oopsies. So hopefully that will make it a little bit more sense. So, you got some time. I went through, I graded your egg drops for those of you who were here. For those of you who weren't here on egg drop day, I sent you a link to the page that has a video for egg drop instructions. It's from a year ago when there was cold days and we did these remotely. Whether you actually drop the egg, that's up to you. If you have an egg at home, if you don't, I don't really care. The intent is to design a device. Whether you drop it or not, that's one of the reflection questions, and then turn that in. Now you can either hand that copy to me or submit that in Canvas. Most of you took care of that though, but there were a few of you that were absent. So let me know what questions I can answer. Again, the front page is kind of a good, I'd say, stopping point. If you want to work with someone, you are welcome to do that.